Thank you very much for joining. So as we probably have an audience here that has not heard of us yet, I will show you a couple of slides, maybe 7, 8 slides about us as a company who is MicroPsi Industries, and then I will show you some use cases so that you also have an idea of, okay, what do we actually do? How does it look like when a robot moves, guided by our AI system? I call this presentation Autonomy for Robots, Tackle Variance in Production. We want to give some autonomy to the robots. We, of course, do that also with AI, like probably everyone nowadays does with AI. I will say it up front already. We have in the hall 10, in the very front, we have a booth, so you can come around later to take a look at this, what I'm showing here in real. Why do we say tackle variance? We are helping companies to automate where they hit some borders or some limits where they actually cannot automate anymore because they say, well, it's just too difficult. If that's a typical example that the customer would bring us where it says, okay, it's hanging on some rack, I need to pick this part, I need to insert it, and then this one is hanging here somewhere. It's hard. For the human, it's super easy to insert it also, but for a robot, it's almost impossible. And this is very typical for what we do. So, first, some minutes about the company and who we are. My name is Maximilian Mutschler. I'm responsible for the sales and engineering team. We are a Berlin-based company. Here's a picture. Actually, this gentleman in the middle, Ronnie, you see him standing at our booth also. But this is the first employees from many, many years ago. Most of them are still in the company, but nowadays we're around 70 employees. So we call ourselves still a startup, but we are a little bit bigger than the typical startup. And what we do is actually we make software. So what we really do is software, and this software helps to combine AI and industrial robots and gives them a hand-eye coordination. We're a team based mostly in Berlin, like 50 people in Berlin. The rest of those 20 are in the US and in Japan. Why am I showing you this customer slide? First of all, to say, okay, we are real, yeah, we exist in production. This is not updated, this is old, but still just to show, okay, there's real customers already who use our product in production. We are mostly active in automotive sector, typical German, American. Then there's a lot of electronics, but also household goods, especially fridges, white goods, appliances. And then, of course, a little bit in other industries, in research and so on. What's the typical challenge? I think I don't need to explain that very long or in detail, but the big challenge is that many parts in manufacturing are already automated. Like typical example, yeah, building cars, welding, screw driving those cars, 100% automated. But all these tasks must be geometrically understood, must need to be fully understood, need to be the same. Very often the robots are not equipped with sensors. But the expectation is that yeah, all of this can be automated. But the reality, if we're looking inside the car especially, is that there are still many human workstations. These human workstations are necessary still because the applications are very complex. That means, like I just mentioned, this cable, it's just hanging somehow. For us humans, that's super easy because we have eyes, yeah, we have hand-eye coordination, and we also have amazing end effectors, and 2 of them. So we can just quickly adapt, although this is a different piece, I can also hold it. Robots don't have that by nature. So what we want to give the robots is the hand-eye coordination. And we do that actually in real time. I will show that later. How do we call our solution MIRAI. So MIRAI is actually in many Asian languages, it means something like the future. So it's different pronunciations, MIRAI. But what we call it, why we call it MIRAI, it's because it's MicroPsi Industries Robotics AI. What you need is a robot, some kind of a vehicle. We need a 6-axis robot. We need also some cameras for input of the signal, and the signal for us is the camera image. And then you have the end effector, depending on the application. Why do we call it autonomy within bounds? Because we want to make something which is still controllable. So you still have it under under control what's actually going to happen with the robot, because AI for many people is still a term which might frighten them. It's not very specified. What does AI actually mean? So we do this within bounds because we want to control the training. So the training of the skill, we call it a skill, is in the end the ability, needs to be within a certain time frame, and we don't want it to learn something that is not desired, like it could happen in reinforcement learning. So what we do is imitation learning, and it can be very, very quick. Within 15 minutes you can train a skill where later the robot will always find this plug, although it's in a different position. What are typical use cases? Typical use cases are for us something related with cables, with sockets, yeah, cable plugging or connector plugging. Then also insertion assembly tasks. So we focus a lot on assembly because in assembly you will often find a part that needs to be picked and then placed somewhere, and that needs to be very accurate. Rack hanging. Rack hanging is something where we also showcase a demo on the other side of Hall 10. Because you might know that there is some companies where some metal pieces need to be coated, need to be painted, whatsoever, and there's a human worker standing, putting metal pieces on hooks. That's also something that we do. It can be even on a slow-moving conveyor. Screw driving, very typical example. Sometimes the screw is in a different position, or the part is in a different position. Leak detection, I will explain that in a video. And also simple pick of very glary objects, for example. All of them have in common that they have variances in the position of the part, in the color of the part, in the shape, in the form, or maybe also in lighting and background. So very important. For many vision systems, it's a struggle that lighting can vary. Sometimes there's light coming in from the side, sometimes artificial lighting, sometimes not. We can just train that. So let me show you some use cases. Time-wise, 7 minutes. Now we have 10 minutes left. I will show you some use cases. That's probably the most interesting. So, there should be a video starting, but if not, then we take the next one and we might go back to this. Okay. This is a use case that we have automated for BSH, Bosch Siemens house appliances. You all know a fridge. At the back of a fridge, there's a compressor. In this compressor, there's some gas, and that's necessary for the cooling. And this gas should not leak out of the soldering areas or the crimped areas of these copper pipes. The issue is that these copper pipes always are at a different position. They are soldered, so there's a different color, a different shape also of the soldering area, but that needs to be checked. And it needs to be precise. Right now, there's a human worker standing with a gas probe and just checking these spots, but that's very prone to errors and also a very tedious task. So let me play that quickly. I will not play the videos in the full length. You can find them on our website. You can see over there where we are a little bit more, but just to give you the real impression. So this is how it looks after it's automated, and here it's before. The human worker has to check these spots, but they are always at a different spot. That's why it's so difficult to automate, and companies have tried this with 3D scanning, with other vision technology, but they couldn't succeed. Here you see actually a training where the human operator just trains the robot. Okay, this is what you need to find. That's the spot that you need to see. And after doing this, it takes them now an afternoon to train a completely new application for a new line of fridges. Actually, you see that MIRAI is now locating always the correct spot. There's always a handover between robot, hard-coded robot system, and then the MIRAI part. But this is running 24/7, and now they even find more failures in those fridges. You see that, okay, now we're approaching, this is the MIRAI part, finding this spot. And you see it over there again, this soldering area doesn't look very neat. It's always a little bit different in shape, color, and position. Next one, very typical. Often we cannot show the real videos. Bosch Siemens was so nice to allow us. If I would ask now the automotives to show the videos here, they would not be happy. But it's the same thing like this. Handling a cable, especially a free-hanging cable out of the air, and then inserting into the socket. And here you see quite nicely that always when the light is on, we are active. When the light is off, it's just robot program. So here the colleague is actually pulling away the cable, not because you would do this in a factory, that you pull away the cables from the robot, but just to show it's very robust. It doesn't need to be in the predefined position. and then it's also inserted in the correct slot. So again, here we find the cable until he holds it still, then the robot can actually pick it, and now also insert it. Here the light goes on again, and for the insertion also this is AI controlled. The laptop is not standing at a fixed position, he also turns it now again just to simulate in the real factory conditions where parts should be almost at the same spot, but they still might vary a little bit, even if it's just a millimeter. You would need the accuracy to actually insert the cable at the correct spot. That's what we guarantee, that's what we make sure. And one more comment, you see now 2 cameras. Those 2 cameras don't create a 3D image or anything, they are just creating 2 times 2D. We work with extremely simple pictures, and all the rest is in the software, the difference, because we don't take measurements. I can explain a little bit about that later, but the big difference from us to all other vision cameras, at least what we've seen and what we still see, is that vision cameras always take a measurement. They scan an object, they measure it, compare it with the CAD data, and then send the robot to an offset. We don't do that. Yeah, one more, hook hanging, wrench hanging, if you want to call it this way. As you see here, a colleague has just simulated a task that we also saw at some customers, and we have a little conveyor belt, and we need to always hang this wrench on the hook. And by the way, this is now a lot of universal robots. We are also compatible with KUKA robots and FANUC robots. But just to simulate, the hook can vary, the wrench can vary. We pick it first and also make sure we hang it on the correct spot. And here it's also, again, movement, but there's a real-time tracking. So MIRAI, our software, enables the camera to find the object in real time. Yeah. And this is done with a very small UR3 robot, so the reach is very limited. So good job from him that he actually managed to complete it there. OK, how do we work? What's our commercial approach? Also to tell you a little bit about this before I ask for questions. We work with a method called customer success planning. So you will never have only the sales guy working with you. If you are interested in finding a solution, you will always have an account manager. That's somebody like me, and a product manager, and also an automation engineer to evaluate together the projects. We focus on target accounts. We deploy MIRAI in production together. We do only scalable projects. So if you say, yeah, that sounds all cool, I have one robot maybe where I could play a little bit with AI. Unfortunately, we are too small to do that because we also need to be efficient with our resources. We say, let's find something where we both benefit from. But then if we agree on this, we hold your hand instead of letting you go and try alone. This picture down low is a beautiful cooperation that we have between KUKA, Mercedes-Benz, and us. And yeah, it's a mixture of different employees there from different companies, which shows this strong bond. Thanks a lot for the time. I can answer some more questions. I have some more backup slides if necessary, but I wanted to keep it short and mostly focused on some real examples of AI on the robot in motion. Thank you.
Thank you, Max.
And again, our booth is over there in the other hall. I'm just repeating that if you want to come around.
Do you have questions? I have so many questions.
Happy to take yours also.
OK, so what does the accuracy look like? Because this is just
accuracy.
Very
so how precise can it be?
Yes.
So what do you think is my answer? Because it's always the typical answer.
I am expecting your... yeah, of course.
It depends. Yeah. And what does it depend on? It depends on the optics that we use. Because the beautiful about our system, or the beauty of our system is, you just see this camera over there. It's now a Ximea camera. We're also compatible with GigE cameras from Baumer, for example. Oh, but you see this camera, and we just have a Fujinon lens on it. So if you say, I want to lift a car door, we use a wide-angle camera. But if you say, I want to insert a needle into a little ribbon, which we also do, then you would use a 50 millimeter, 100 millimeter magnification camera. So it really depends on what you need. And the answer is, and the correct answer is, the accuracy is 1 pixel. Yeah? Because 1 pixel of the resolution that we see is in the end the accuracy that we can reach, and it depends on how big is the pixel. And it also depends on the training. I didn't say anything now about how do we train this, because the training is super easy. It's radically different from what other cameras do. But if you're interested, I can show a little bit more about that also on our booth.
Yeah, that would be really nice, because this is extremely cool what I just saw, and it was like, because there are so many variables as well. So there is orientation as well. So in your laptop and USB cable example.
Yes.
So there's definitely, I mean, it's not so complicated, the orientation for a human at least, but if you understand, I mean, the robot could have really done it vertically, or could have at least tried, but it did not even try.
So there's always this, let me explain again, that we only take care, and this is a lot of show. Yeah, what we do here is doesn't really look like production. That's also showcase to impress people, and then later tell them, okay, but if we make this production ready, you will hardly see what we do, because it's a very small correction only. So there's always a handover. So we would, if I want to pick this, you would know roughly where it is. It's either here, there, or there. So I would have the handover pose here, and then only let MIRAI correct this little part. Yeah, only let this little correction, or let me call it like this, correct like this. So there's only a very small part that we, in the end, actually really correct.
Okay, and also at the insertion level. I mean,
again,
you could have.
Once you know, okay, my object, my target is somewhere down here, and I'm holding this plug now.
Yes.
You will not let start MIRAI here and look for it and look for it. That doesn't make sense. You would know, okay, it's somewhere here, and I just let it correct for this last centimeter or last couple of millimeters. Yeah.
Sure. I mean, okay, I think we still have 4 minutes, and I think for the live broadcast, we really have to start at 20, the next one.
No problem.
But I can keep going. This is my field. I personally work with standards. Also, OPC for robotics is also one of the things that I have to do. So this, like, it's extremely cool what you guys are doing there, and I'll definitely go to your booth after the show, after this session. But really cool. But you said skills, right?
Yeah.
But what I have heard the term skills quite a lot. And when we talk about skills, is it something that you can just bring together and then just start, or?
Yeah, so we always have, for the robot platforms that we're integrated with, and that's only 3, because that was driven by demand. It's a lot of work for us to integrate, because we need a real-time interface to talk to the robot. We don't just send him on an XYZ coordinate. We need to talk to it in real time. So there's always, for the platforms where we are integrated, there's a, for UR, it's called a UR cap. For KUKA, it's called a COP file. Basically, it's a plug and play. So you will not feel as a user that there's a lot of stuff done in the background. But yeah, correctly. So that's what we do. There's a plugin directly.
Perfect.
I can, if you want, I can, and if there's 1 more minute to fill, I can actually. It's not a beautiful slide, but I believe it's a quite important slide, showing the differences to normal cameras again. Because I just want to highlight again and again, we don't take measurements. That's such a big difference, and it then allows us to handle much more complex parts. It allows us to handle parts with black on black, white on white, a black hole on a black part, a mirror on a transparent surface, whatsoever. It really doesn't matter. As long as the human can see it, we can do it. We don't take measurements. We don't take measurements. We don't take measurements. So that means it's really, really important to emphasize on that, because that's the big difference to all other systems. And that means also that the path planning is during the execution. So actually, we only do relative movements, and we can adapt the path while we are approaching the object. That means sometimes it's vibrating, sometimes it's hard to do a good scan or a 3D picture of such an object. Yeah, it's very, very difficult, and these are things that we can actually take care of. So should I say more?
I mean, if you have more to share, you can always share more. So is it based on point clouds then?
No, not at all, exactly. So we don't take any CAD data, point clouds, no measurement. We just scan the real object as it is. And we actually work with very low resolution. So the image that we take, usually our users are surprised that they say, okay, that's the image that you work with, and you can achieve the accuracy. It's 300 pixels times 250 pixels, so it's really, really, really small. But it's still enough for accurate execution. I can check what else. I would have some more examples here. Yeah, that's maybe. Oh, why is there no video? There's no video. There would be more contour following, following the contour of a sealed bag, for example. It's not a video, it's not playing right now, unfortunately, is it? Oh, yeah, it is. No, yeah, I will just show you some more. Until you say the time is up and we
It is. I mean, I can already welcome the next speaker, but thank you for your time. It was a pleasure, very much. But you will see me soon.
Cool. Thank you.
Thank you so much.